Alright, so let's go ahead and jump in and get started on something that should be hopefully familiar, at least from Algebra 1 and beyond. This concept is called lines. Lines are pretty important in calculus. Most of calculus focuses on this concept called local linearity, meaning that even if a function curves and we were to pick a point to say very, very local to a point, the function behaves very much like a line. So, for example, if I graph the functions of y equals sine of x and y equals x on a calculator, these are obviously not the same function. However, if we stay very, very close to the point of 0, 0, these two functions are very close. So, if you don't believe me, let's go zoom in on 0, 0. Okay, so I've jumped over to Desmos. I've graphed my line of y equals x, which is in red, and I've graphed my sine of x, which is in blue. So right now these don't look like the exact same function. Sine of x looks like anything but a line, but again I said, hey, let's pick a point that they are almost touching, if not touching at. So I'm picking that point of 0, 0. I'm zooming in. Alright, blue graph, which is my sine graph, still looks like a curvy boy, so I'm going to zoom in even closer to 0, 0 to see if I can make this look any more like a line. So, zooming in again towards 0, 0. Alright, so if I didn't know what this graph was before, I would probably guess that this blue is probably a line. I'm not gonna lie to you guys. It looks very much like a line, especially at this point of 0, 0, as I've gotten closer and closer and closer. This is definitely becoming more and more line-like. So this is what it means by local linearity. At a certain point, both functions are going to look like a line at some point. No matter how curved it is, no matter how straight it is, at some point, if you zoom in close enough, it is going to look like a line. Alright, let's jump back to... So, jumping back to the notes here. So again, getting very, very close to a function will give you a line. Alright, so let's talk about slopes of a line, because that's pretty important when talking about those things. So we've got a couple different types of lines. The slope of a non-vertical line is given by that change in y over change in x. Notice that those triangles just mean change. That's that Greek letter delta, if you don't know or don't remember. So, change in y over change in x back in Algebra 1 was just that y sub 2 minus y sub 1 over that x sub 2 minus x sub 1. Keep in mind that a vertical line has undefined slope. It's straight up and down. So you would get something over 0. If you divide by 0, your brain goes boom. It's a bad day at the office and in math class. And then a horizontal line, which is the one that's straight across, has a slope of 0. Parallel lines have slopes that are the exact same. Meanwhile, perpendicular lines have slopes that are negative reciprocals. Didn't mean to... Alright. We will be best served in calculus if we think of our slope as the rate of change. And the slope between 2 points is often going to be referred to as the average rate of change. Alright, other parts of a line that we should be familiar with at this point are the different equations of lines. The first equation of a line that were used in algebra was probably that slope-intercept form, which everybody gets drilled and killed into their head, which is that form of y equals mx plus b. Where the slope is the m and the y-intercept is that b. In calculus, it's actually easier most of the time to go with the point slope form, which we talked a lot about last year in pre-calculus, which is that y minus that y sub 1 is equal to m times the quantity of x minus x sub 1, where the point is that x sub 1 comma y sub 1, and the slope is still m, just like slope-intercept form. And to write an equation of a line, all you need is the point and the slope. Another format to write an equation of a line is called standard form, or sometimes it's called general form. I just don't hear it called that as often. This is easy as ABC, literally AX plus BY is equal to C, where A is always positive, and with the X, B is not always positive, but that's alright. A and B nor C are fractions, all that kind of good stuff. It's just not as commonly used, to be honest. Most of the time in calculus, we're going to be using point-slope form or slope-intercept form. Alright, so example 2, which of these equations has a y written as a function of x? So all that means is that y is by itself, so the only one that actually has y by itself is that slope-intercept form of that y equals mx plus b. Alright, point-slope form is written as that y equals m times x minus x sub 1 plus y1 if we want it written as y as a function of x, because y is written as a function of x literally just means, hey, write it as y equals. So literally the only thing we had to do is add that y sub 1 over to the other side in order to get that point slope form in that general form. Cool. Not tough. We're not into the tough stuff yet. It's calculus. It's gonna get harder, and that's okay. We're here for it. Alright, the next example says, hey, write the equation of line passing through the point of negative 2, 4, and having the following characteristics. The slope is 7/16, so it gave us a point and a slope. So hopefully we're using that point-slope form. So we've got y minus y sub 1, which in this case, my y sub 1 is going to be 4 this round, is equal to m, which already gave me that slope of 7/16, times x minus x sub 1, but I've got a negative in for my x, so I can just go ahead and write plus 2. Cool. Alright, so parallel to the line of 5x minus 3y is equal to 3. So it's given us in standard form. The cheap way to figure out what slope is without having to put this in slope-intercept form like a lot of you guys like to do. Cheap way of finding the slope is just going to be negative a over b is just going to be my slope. So that's going to be negative 5 over 3. Negative 3, sorry. So all in all, my slope should be 5 over 3. So, cool. I have my point. I've got my slope now. So I've got y minus y sub 1, which is still 4, is equal to 5 over 3 times x minus x sub 1, which should still be that too. Alright, so if we can do a parallel line, we can also do a perpendicular line. Works almost the same way, but we just so happen to already have the parallel slope. So if we've got the parallel slope meaning the same slope, guess what? All I have to do is negate that and flip it to find my perpendicular slope, which should be negative 3 over 5. All the rest of it should be darn near the same. So I should have y minus 4 is equal to negative 3 over 5 times x plus 2, and we're golden. Next bit, I'm passing through the origin. Passing through the origin just means, hey, I'm going through the point of 0, 0. So going through the point of 0, 0, what I'm going to do is I'm going to call this particular point up here x sub 1 and y sub 1. And then I'm going to call my 0, 0, 0, 0, which is going to be x sub 2 and y sub 2. So then I've got my y sub 2 minus y sub 1 all over x sub 2 minus x sub 1. So I've got 0 minus 4 all over 0 minus negative 2, which is just going to turn into plus 2, which is going to give me negative 4 over 2, which is just negative 2. I hope you guys aren't surprised by that in the least. So I've got my slope. I can pick any point that I want. I'm probably going to go ahead and choose my 0, 0. So then I've got y minus y sub 2 in this case, which is just 0. So leave that just as y is equal to my slope, which should be that negative 2. And then negative, why is this not writing? So I've got my negative 2 times my x minus x sub 2, which is just 0 again. All in all, I should eventually just get y is equal to negative 2x. Alright, my last one I've got is that parallel to the y-axis. Parallel to the y-axis just means, hey, it's got to have the same slope. I know that my y-axis runs straight up and down. And at this point, I should know that my straight up and down lines start off as x equals. And then from here, it's just literally looking at that point that I'm given and looking at that particular x value, which happens to be negative 2 on this problem. And with that, we're done. Have a great rest of your day. I will see you tomorrow. I will not be reading all of the notes all of the time to you guys because I want these videos to be very quick. And I don't want to just be taking 45 minutes to read straight off of a piece of paper, so I will probably just do example problems and maybe summarize some of the stuff that's said, but I'm not going to read these all to you. But like I said, have a great day. I'll see you in class.